Okay, good morning everyone. Welcome to lecture 19. So, of course, we had a plan to make an offline lecture once again. However, due to one COVID-19 positive case in our class, so unfortunately, we turned into the online lecture today. And for next lecture, lecture 20, I have not decided yet. So if you have any symptom or any, symptom is not enough. If you have any positive result for your COVID-19 test, then please let me know. Then I will make a decision whether we will go further with this online lecture or come back to our classroom. So please let me know. And I wanted to check your attendance. So I will check your attendance from now on. 이재혁 씨, 고하늘 씨, 심준호 씨, 이승빈 씨, 그리고 이정태 씨. 네, 고하늘 씨 안녕하세요. 심준호 씨 안녕하세요. 이정태 씨 안녕하세요. 이승빈 씨 안녕하세요. Okay, let's go to the next page. 이충아 씨, 정상아 씨, 홍주표 씨. 네, 이재혁 씨 안녕하세요. 네, 이충아 씨 안녕하세요. 오케이, 정상아 씨 안녕하세요. 홍주표 씨 안녕하세요. We will move to the third page. 김민선 씨, 그리고 김유신 씨, 배민열 씨, 배서령 씨, 서하연 씨. 네, 배민열 씨 안녕하세요. 김유신 씨 안녕하세요. 서하연 씨 안녕하세요. Okay, now we move to the last page. 조대현 씨, 최승규 씨, 김성수 씨, and Mr. Manicure. 조대현 씨 안녕하세요. Okay, good morning. 최승규 씨 안녕하세요. 그리고 김성수 씨 안녕하세요. Okay, we are all set. Okay, so do you have any question about our previous lecture 19? So I remember that we have finished our lecture contents about the MOSFET's IV characteristics. So at the end of our previous lecture, we had some shortage of remaining time. However, anyhow, we will just move on, and if there is something to be discussed, then I will come back to the MOSFET part once again and explain that specific feature of MOSFET IV characteristics. Okay, so before starting today's lecture 19, if you have any question, then please let me know. So otherwise, I will start today's lecture. There is always a certain delay between my question and your response, so I will wait for a while to receive your questions. Okay, so if you have no question, then I will just move to the main contents of lecture 19. So as announced in the previous lecture, from now on we will start a circuit which has two components. Or two components means that one is the MOSFET, the M MOSFET, and another one is a resistor. Of course, we will consider voltage sources, but they are just given. So we'll just consider these two components. Okay, so why don't you just start immediately? So now we have a MOSFET. So here we have a MOSFET symbol. Yes, and this is a source, and this is a drain, and this is gate. Oh, of course, we have a hidden terminal, the substrate or the body, but it is assumed that substrate or the body is also connected to the source and connected to the ground. So in this case, yes, here we have a MOSFET, and we know that when we apply VG and VD, then important quantity is voltage difference between this gate to source, and voltage difference is drain to source voltage. So depending on the relative magnitude of Vg and Vd, or relative magnitude to the threshold voltage, we will have quite a different behavior of our transistor. As I told you before, most important thing we will have to check is, yes, whether that transistor is actually working as a switch. Okay, so if we have our drain bias as a low value, then we will have this behavior. There will be certain almost piecewise linear behavior, so we can clearly define the threshold voltage. So below threshold voltage, yes, we have no electrons collected the channel region, and beyond that threshold voltage, of course, we have a lot of electrons which can be used for current conduction. So the Vd equal to small voltage, that condition is just to check whether you have a sufficient amount of electrons or not. Okay, and in actual application, Vd is low condition is usually not used. So usually Vd is high enough. So because Vd equal to high voltage, that is the condition for maximizing the drain current. So we usually use this condition. So then we will have also similar graphs, but much higher values. So this is corresponding to Vd equal to a high voltage, and this is the case with a low voltage. Okay, so this is so-called input characteristics, and we have to also consider output characteristics, ID versus Vd. So then we will have a typical curve like this. Yes, there will be certain parabolic curve here. After that, there will be such a saturated value. So this is corresponding to saturation current, and of course this operational region is also called as a saturation region. And also here we have another one which follows parabolic behavior as a function of Vd. So this is typically called as triode region. Okay, this is it. And if we further reduce our constellation, then here we can see that almost linear behavior. Okay, at the beginning of our curve, at the beginning it just looks like a linear curve. After that, its derivative is now diminishing, and eventually get flattened here, and it enter into saturation region. So this smaller range is called as linear region. Okay, but anyway, this is the separation of operational regions. And yes, so if we ask ourselves the value of this point, so how can we obtain this one? So this point is corresponding to our two expressions for drain current. So we have introduced one expression which is valid for the triode region. It takes certain second order term of Vd and linear term of Vd. So that's the reason why we have a parabolic behavior. And beyond a certain voltage, beyond certain drain voltage, then we will have just a saturation current, and that is the point. That means that this point is the point where two different expressions are meeting together. And this condition was, if you remember correctly, then this Vd is corresponding to Vds is Vgs minus Vth. Okay, so now usually this number, the difference between gate voltage with respect to threshold voltage, this is excessive voltage to turn on our transistor, or actually this amount of voltage is effectively used to drive our or collect our electrons. So it has its own name, and we call it as gate overdrive voltage. Okay. So now it becomes clear that in this long channel device, so the knee point between this triode region and saturation region is given by this point where the drain bias voltage becomes equal to the gate overdrive voltage. Of course, the saturation current is simply given by ID saturation is given by this number, mu n C ox W over L, and half of VGS minus VTH squared. Okay, so you can easily remember this expression, because you know this is just obtained by when you insert this condition into your triode expression, then you will immediately get this expression. Okay, now you have understood the behavior of your drain current as a function of gate voltage and drain voltage. Of course, we have not discussed about the case where gate voltage is even lower than threshold voltage. In this case, we believe that the channel is not formulated and there is no electrons between source and drain, so it is very difficult to allow any kind of current conduction. Of course, you know that ID is not exactly zero. If we have to find out the real value, then of course ID would be slightly larger than zero. However, this amount of ID is much smaller than the ID considered in the right hand side, so we just neglect that this small amount of current conduction. Okay, so do you have any question? So I'm afraid that since we are now in online, so it is difficult to uh, listen your question. So however, please anytime please interrupt me if you have any question. So up to now we have discussed about a single device. In this case, what we have assumed was, okay, the values of VGS and values of VDS, they are known to us. So we just set these numbers as a granted or known, and we try to just calculate a drain current. But now think about a little bit more complicated case. Okay, now we introduce a resistor R, so connected to the drain. So voltage source previously attached to drain terminal is now removed. So we have no predefined value of drain voltage. Instead of that, we just add here, so VDD into our this upper part. Okay, so from the viewpoint of our N MOSFET, now voltage source is not directly connected to its drain terminal. Instead of that, there is indirect connection between its drain terminal and VDD through certain resistor R. So we will think about this case. Actually, this is, this is a quite simple circuit. However, it already gives you a very interesting behavior. So we will talk about this property in this lecture 19. Okay. So once again, if you have any questions, then please leave your messages. I will continuously checking your chatting log, and if you ask me any question, then I will be very happy. Okay, then now think about this so simple, maybe one of the simplest circuit we can imagine, having only one transistor and only one resistor. Okay. Then our goal is now changed. So previously we had VG and VD simultaneously. So we knew it. So previously we knew VGS and VDS, and we wanted to know ID. But now we only know VGS. Still, we apply certain voltage to it, and since it means that drain terminal is not directly connected to the VDD, we have no idea about the voltage, drain voltage. So since drain voltage is not known to us, of course, ID is not known to us. So our major concern or major interest will be what will be the drain voltage. So now from now on we will use this gate voltage as a input. So we introduce a certain signal to our gate terminal in the form of voltage. Okay, now voltage will be regarded as a signal. So think about two different domains like digital and analog. So if we are working in the digital system, then how can we implement our information or our signal as a form of voltage? Of course, we need implement 0 and 1, logical 0 and logical 1, and it is not that difficult for you to understand. This logical 0 is corresponding to 0 volt, and logical 1 is corresponding to VDD, the highest voltage we can imagine in this circuit. Okay, then yes, so whether 0 or VDD, that can be two possible input voltage to our gate. And in the case of an analog domain, it is not that way. So we have to introduce certain small fluctuation. So we have to introduce small fluctuation of our signal. So as a function of what? A function of time. And the deviation from certain predefined reference value. Let's say that this is V left, then the difference that is interpreted as a signal. So for example, if we are looking at this part, then signal strength is weak, and here we have strong signal. So that is two ways for treating our information as an input voltage. Okay, so if you have any question, then please let me know. But anyway, we have the input voltage. Then what will be again the output quantity? So of course we can think that either VD voltage or ID drain current can be an output quantity. However, we will also consider this voltage as an output one. So now we understand in this system we have a certain voltage input. Yes, so we apply certain input voltage, and we have certain black box, and after that we will get once again certain out value. Okay, so think about this one. Of course, this lower bar here, lower line, is used for our reference value, so it can be regarded as something. So for example, in the case of a digital system, we just say that this V in is just reference the difference between our gate voltage and source voltage. Okay, this is just VGS, and in this case we can treat this drain volt, the difference between drain voltage and source voltage as an out voltage. So, and in the case of, for example, another one, another means that another analog domain. So in this case, input signal is not VGS minus VS itself, but it is more suitable. Consider certain reference voltage. So certain reference voltage. Also, we will introduce certain reference voltage for our output signal. Of course, this and that, they can be different. Usually they are different. Okay. So anyway, this small signal input is converted into small signal output, and we will use it for our signal processing. Okay. So do you have any question? So let me summarize. Let me summarize the discussion up to now. So after reviewing our previous lecture, I just introduced a simple circuit which has one MOSFET and one resistor. After that, I just explained that in this case, we wanted to have the voltage relation of this simple circuit. Input is a voltage variable, and also output is the voltage variable. So we wanted to calculate their behavior. Of course, if we follow this analysis, then finally we will get this form. Simply speaking, so VDS is expressed as a function of VGS. So, for example, we will eventually have this form, VDS and VGS, and we will draw this graph. Okay. Then what will be the range of our input? Input, yes. So input can vary from just to 0. Okay, I see. And also, what will be the maximum value we can apply to this gate terminal? Of course, it is limited to what? Yes, VDD. Okay, so we will consider the behavior of our simple circuit as a function of gate voltage within a range of 0 to VDD. So we will draw what will happen to this case. For example, you can imagine yes or yes or yes. Any behavior can be expected. However, let's just make a further investigation on this relation. So are you all with me about our intention? So our intention is to calculate this VD versus VGS behavior. Okay, so if you don't have any questions, then please let's proceed. So the simplest one would be the case where we have just 0 gate voltage. Yes, think about this one. Now we have 0 gate voltage. Now, yes, this is equal to 0 volt. Then what will happen to this system? Now, transistor. So in this case, ID is just given as 0, although I use this approximation symbol for this part, but you know that this is almost 0, so we can safely say that this is just equality in our engineering sense. So simply speaking, when we just set our gate bias as 0 volt, then this transistor does not conduct at all. Okay, so then think about this one. Here we have a certain circuit node where two circuit elements are meeting together. What are those two circuit elements? Yes, one MOSFET and one resistor. So in this case, of course, we have to satisfy the KCL. So simply means that if we say this current, the current flowing through the resistor is denoted as IR, and the current shown here, the current flowing through the drain terminal is ID. Of course, the ID means that the drain current of our N MOSFET. So if we have this direction, so one is incoming from the viewpoint of our circuit node, and one is outgoing from the viewpoint of that circuit node, then our KCL simply says that IR, so incoming one, is equal to our outgoing one, VD. So this is generally valid for any cases. So right now we are considering the gate voltage is equal to 0. However, even when we have different gate voltage values, but we will have this KCL. Okay, that is quite general. Of course, we have to think about it. So if we have this form, then KCL, then especially when gate voltage is equal to 0, then we know drain current equal to 0. So quite easily we can find that IR should be 0. So think about a certain resistor. It has a finite R value, fixed R value, and we have to exactly 0, almost close to 0 current. Then what is the condition for vanishing current for a resistor? You know that in order to have vanishing current, the voltage difference across two terminals of that transistor should also vanish. It means that if we have a certain voltage, for example VDD minus 0.1 volt, then this difference 0.1 volt will drive our resistor and there will be current. However, that is contradictory to vanishing drain current condition. So it's not possible. No. So the only way we can satisfy the KCL is simply, yes, this drain node, drain voltage should be exactly VDD. Okay, so if we have the voltage exactly matched to VDD, then from the viewpoint of our resistor, no voltage difference is applied, so I do not conduct any current. That's the one thing. And from the viewpoint of our MOSFET, although drain is highly biased to VDD, so the drain to source voltage is also again VDD, that is high voltage. However, since gate is biased to 0, although we have high voltage, we don't have any current conduction. Okay, so now you can understand the answer of our curve. Well, the answer of our output voltage would be just here. So this point is corresponding to 0 volt and VDD. It is quite easy to understand. Okay, so could you please show your responses? So all of you have understood this simple explanation. So simply speaking, when we turn off the transistor, we have no current conduction. In order to satisfy this condition, our output voltage should be 0. That is my explanation. So please leave your message whether you have understood of my previous explanation or not. So since this is the important one, so if you don't understand, then I have to repeat it again. So please everybody leave your message. Okay. Okay. Good. So, okay. Thank you. So simply speaking, it can be just considered as this conceptual view. So if we just neglect the transistor which is turned off, then it can be regarded as this form. Yes, and this is called as VD. Where is the transistor? Since transistor does not conduct at all, so electrical sense, there is nothing. There is no way for our electron current to follow. So in this case, this is just a dead end of our circuit. So the voltage here will be exactly copied. So we will have just VDD. Okay, that is the simple explanation. So then I have one further question to you. So I think that this is not that difficult to understand, but you have studied a little further. So please think about your N MOSFET. So now you have N MOSFET, and it has this condition. So Vg equal to 0 volt and Vd equal to VDD. So could you please leave your answer to my question? What is the current for this boundary of this bias condition? Gate is 0 and drain voltage is highly driven with VDD. So we have studied that name. So what was the value? There was a certain name for this drain current. Do you remember? So if anybody remember this name, so please leave your message. Yes, you're right. So yes, you're right. Thank you. So now you understand the importance of Ioff. So in this case, so the ID, drain current calculated at or measured at this bias condition is called as Ioff. So we have Ioff condition. So now it becomes clear that our current in this case is not exactly 0, but now it becomes just I of state current. Then please think about this one. Instead of this exactly 0, so now we have, although that is quite small, so now we have I of. Then KCL is still true, but ID is no longer 0, but now it becomes instead of this exactly 0, now we have I of. So resistor current should be also I of. So in order to support this I of, what will happen? In order to support this I of, then we have to have really small, although quite small, but the voltage applied to our resistor will be now given by R times I of. Okay. So once again, I want to stress that I of is really small in good, reasonably good technology. So this voltage drop would be quite small. But anyway, it is certain that if we have considerably high I of, then this system will allow non-zero current even when we have zero input bias, input signal, input voltage. So it is a non-ideal case. So we wanted to have really zero current, but yes, if we have I of, that is far away from our ideal case. So that is the killing point for our modern technology. We will consider this concept again and again. But point is, although we say that when transistor is off, drain current is 0. Yes, in a rough sense, that's true. We have much smaller current than the on condition, the beyond the threshold voltage. But point is, although that is so small, but that is not exactly 0, and that will introduce a certain problem. So what is a so-called certain problem? So let me just think about in this way. Now, let's assume that we have applied 0 voltage to our input. Then we have now I of our transistor. So overall, the system will allow this I of. Okay, starting from this VDD line, ending at this ground line, there will be the current flow, its magnitude is I of. Then you know that I sometimes give you some homework problems about calculating the power dissipation by certain circuit element. So the answer was always simple. So just multiplying the voltage difference and the current flowing through that circuit element. So quite similarly, if we consider the power dissipated by this combination of resistor and MOSFET would be now become what? So could you please answer? So if we have this configuration, what will be the power dissipated by this system? So, although the answer is quite simple, but I wanted to check whether you have understood this simple fact. So, could you please leave your message? So, okay. If you don't understand, then please let me know. I can repeat my explanation. Okay. Yes. Thank you, Mr. Go. Yes, that's true. So the power dissipated by this system would be, yes, simply, thank you. So will be just VDD multiplied by I off. Okay, so now you feel that, although VDD is around, for example, 0.7 volt or certain volt, 1, 2 or something like that, since I off is so small, so small, so actually the product between VDD and I off is really negligible number. Yes, yes, that's true for a single device. However, please note that in integrated circuit in these days, we have really several billions of transistors inside our system. Let's just say that we have introduced 1 billion transistors or 1 billion same copy of this system. This system is just copy and pasted into our system, and we have found 1 billion copy. And for all input gate value, we just apply 0 and just measure the power dissipated by this collection of 1 billion systems, 1 billion circuits. The answer will be the power dissipated by this total system will be just VDD Ioff. Yes, that is quite a small number. However, we have to multiply 10 to the 9 of billion, which is corresponding to number of transistors. So, although this number is so small, but this multiplication factor is so drastic. So the calculated power can be quite considerable. So that's the point. So, so as a design device engineer, people try to minimize I/O. Otherwise, even though you have turned off your system just consume certain power only due to the imperfection of your transistor. If your transistor is completely turned off, then that power dissipation will not appear. But only you have introduced imperfect devices which is not completely turned off, you have conservable power consumption. Okay, so that power consumption is a real big deal, the killing factor of circuit design. So that's the reason why we have to care about the reduced Ioff value. Okay, so if you have any question about in this aspect, then please let me know. But anytime when you have a question, then you can interrupt me. So now let's move to slightly higher gate bias. We have 0, VDD. Then now let's go to a slightly higher voltage. However, let's say that this gate voltage is still lower than our threshold voltage. Then what will happen to this guy? Yes, now our transistor is still turned up, although you know that the current itself is significantly increased. However, since Ioff was so small, still we have so small current. So if we just consider it as negligible, then now we can say there will be almost no change in output value. So are you all with me? Then let's go to certain voltage. Yes, for example, I will just use this one as a threshold voltage of this system. So let's say that this is corresponding to our VTH. So this curve will be almost flat until the gate bias reaches to what? To VTH. So now we can say that even when we have VTH as a gate bias, now transistor is just ready to turn on. However, it has almost no carrier up to now, so the current would be quite small, and we still have VDD. So are you with me? Then up to now, what we have learned is quite simple, and now it means that okay, we will have just a straight line here. So below threshold voltage of our N MOSFET, the output would be just VDD. No difficult discussion up to now. Then now let's go to beyond threshold voltage. So it will be quite interesting. Yes, now we have here. Then now we understand, since gate voltage is higher than threshold voltage, now we have to consider either triode mode operation or saturation mode operation. What will be your guess? So now, since gate voltage is slightly higher than gate voltage, then at least our transistor is now turned on. But is it in the saturation, or is it in the triode? So think about this one. This is the output is the drain bias. So now if we have a smooth transition of this curve, then we can say that maybe VDD is close to VDS, the drain bias voltage, is close to VDD. Then when we make a comparison between gate overdrive voltage and VDS, which one will be higher? So this is just a small number, because we are now considering a point where the gate bias voltage is slightly higher than threshold voltage. So gate overdrive voltage shown here is quite small. Okay, So now we can certainly say that at the beginning of our curve beyond the threshold voltage, it is guaranteed that our transistor is operated in the saturation region. So by assuming the saturation region, now we can follow this form. First of all, we have to once again rely on the KCL. Okay. So then let me just explain or explicitly write down the KCL. First of all, I have to calculate the IR. Then IR is given by the voltage difference divided by resistance. So what is the voltage difference across the resistor? It is quite easy to say, because VDD is the bias voltage for top terminal and minus VD or VDS anyway. So that will be once again the difference. Okay, so so I'm afraid that maybe some of you are confused by this VDD and VD. VDD is the maximum voltage we can have, and VD is just drain bias voltage. So instead of this VD, let's call it as output voltage, for example. Of course, this output voltage is drain voltage. So let's say out voltage. Okay. Then this form, the left-hand side form, IR form, that is generally valid. But for right-hand side form, ID, we have to consider the non-linearity of our transistor. But now we know that this transistor is working in the saturation region, so that's the reason why we can safely write down in this way: half of mu n C ox W over L, and here now we have something, but that something is simply given by VGS minus VTH. When you have a look at the right hand side term, there is no dependence on VDS or equivalently V out. So simply speaking, so your V out or VDS, VD can be easily calculated in that way. So let me just do simple calculation with you. You can do it together with me. Now, so R is multiplied to both parts. So we will just have R here. Then now we can write down V out is given by VDD minus half of certain fixed numbers, mu and cox w, where they are all given numbers, and VGS minus VTH squared and R. So how do you draw it? Could you please draw it for your understanding? So I will just draw it. So it will just oh, sorry. I wanted to make it beautiful, but okay. Let me do it one shot. So, sorry about that. Let me just try once again. So anyway, you know what I mean. So I'm trying to draw certain parabolic curve which is just inverted or heading the downward, yes, there will be certain graphs like this. Of course, you know that, for example, this one, for example, negative VDS never appears. So why do we have such kind of thing? This will be just violating of our assumption. So we will consider it later. But for example, if we just assume the gate bias voltage, input voltage larger than threshold voltage, and by assuming the saturation mode operation, then we will have this behavior. Okay. So then why do we have this strange behavior? Is of course we have assumed one thing. The assumption was saturation mode operation was assumed. So of course, at the beginning, when the gate voltage is small enough, then this is good. But as you can see in this curve shown here, so although we start from the some point which has quite high VDD, as gate voltage is increased, now drain voltage is rapidly reducing. At the same time, the gate overdrive voltage is now increasing. So what was the condition for having the triode region, or what was the knee point? The condition was the gate overdrive voltage is equal to VDS. So let me just think about this one. If we have any point here, for example, then what is the gate overdrive voltage? The gate overdrive voltage is given by this difference. Then what is the drain voltage? Of course, in this case, this will be the drain voltage. Of course, you understand when we make a comparison between these two lengths. Oh, now we can say, at least for this gate bias voltage, we are still in the saturation region, because this height corresponding to drain voltage is much taller or longer than this width. So it is sufficient to have saturation mode. However, let's think about another case. So starting from this VTH, now let's try to draw a line whose slope is just given as 1. So this one is slope equal to 1 curve. Then let's think about the crossing point between this inverted parabolic line and one straight line. So of course you can find this crossing point here. Then what is the physical meaning of this point? Yes, the height is corresponding to the drain voltage, and this width is corresponding to gate overdrive voltage. So since the slope is 1, it means that at this point, now our transistor enter into the triode region. So if we go beyond this bias point, for example, yes, for example, this one or this one, it is now certain that the transistor is no longer working in the saturation mode, but it will work in triode. Okay, do you have any questions? So we have only 10 minutes left, so let me just consider the final one. Okay, so what is the exact value of that point? So you have to calculate it, but if we assume now triode mode operation, then instead of this, oh, sorry, instead of this form, now we can write down in this way. So mu n c ox w over L, and now we have VGS minus VTH, and here we have a drain bias, but here drain bias is denoted as V out and minus V, sorry, we have one leading coefficient here, half of V out squared here. Okay, so now you can easily understand, this one is now V out, and V out. Yes, we have V out for second order polynomial for our V out, so we will have different behavior than this guy. Okay, previously V out was a second order polynomial of gate over drive voltage. Yes, however, now VGS appeared here as a coefficient of our V out term. So of course you can try to draw it, and the result, the curve will just looks like this. So it never go below 0, so it never become 0, and you will have this behavior. So this is the can I say, this is the behavior of our system, which has only two circuit components. One is the MOSFET and one is a resistor. So the input and output characteristics can show much more complicated behavior than we can naively expect. So this means that this curve is obtained from our nonlinear behavior of transistor. If we have just two serially connected resistor, we never obtain such kind of behavior. Since we are now using the MOSFET, so we can have this quite a complicated behavior. So now we have only a few minutes before the end of lecture 19, but I wanted to introduce very important conclusion or remarks on this system. Okay, now you have full knowledge on the input and output characteristics of this simple system. Yes, so when you change your gate bias voltage, then now you can change your drain bias voltage. So let's see about the application of this circuit in a two ways. Two way means that once again, digital and analog. So when we consider digital, so what was the used voltage range? So there was two cases, 0 volt or VDD. Then think about this one. If your input is 0, then what will be the output? Yes, you will have this point. And when you have VDD as your output variable, then where will be your answer? Yes, this will be the output. Of course, yes, we are quite certain that we have a 0, VDD. However, for this point, although we have a VDD as an input, but you know, you have no idea about what is it exactly. But you know that this would be anyhow close to 0, although not exactly to 0, but yes, that will be just, for example, 0.1 volt or 0.2 volt, so much smaller than VDD. So what you can expect from this input-output characteristics of this simple circuit is when you have input 0 volt, yes, certainly you have VDD. So when you have VDD, then you will have output which is close to 0 volt. Then instead of this voltage, let me just introduce a certain notation, logical notation. In this logical notation, we just label them as logical 0 or logical 1. Could you please do it? So if we introduce logical 0, then it will generate logical 1. And if we introduce logical 1, then this circuit will generate an output which is close to logical 0. Of course, we know that this is a digital system and the output which is close to 0 is now interpreted as just 0. So we can safely just neglect this similar approximation. So now you understand, when you insert 0, you will get logical 1. When you insert logical 1, you will get logical 0. So you know that that is corresponding to a logical operation. 0 is converted into 1. 1 is converted into 0. That is the logical NOT. So 0 to 1, 1 to 0. It means that you have implemented the NOT gate or inversion gate by just combining these two components, resistor and MOSFET. Okay, so this is the concept or the remarks we can have in this digital scene. And if we go to analog scene, then actually this value itself is not that important, but still we wanted to have this component maximized. For example, we wanted to maximize the change of our output voltage with respect to our input voltage. If we change input slightly, then we wanted to have the change of output following that input fluctuation. So in this case, just like in the previous lecture, what we have to care is not the value itself. In this case, we have to care about the, how can I say, the slope or derivative. Then, of course, this curve is going downward, so always it has a negative slope, but which one shows the maximum absolute derivative? When you take the absolute value, then where do we have the maximum derivative? For example, this one, or this one, or this one. Obviously, you know that this part is corresponding to the steepest slope available for your input-output characteristics. So when you use your system as in the analog application, then your operation point should be around here, not here and not here. So are you with me? So now let me just summarize my talk. So we have already 1 minute delayed. So we have studied very simple circuit. It has MOSFET and resistor, and we have studied input-output characteristics, and this circuit can be used both of digital domain and analog domain. Okay, so in the next lecture we will continue our discussion. If you have any question, then please send me an email. Thank you and bye.